Hi, I'm Rob, and I'd like to welcome you to the next video in the AI Engineering Hands-On playlist on the Cumulus Cycles channel. In the last video, we created some Jupyter notebooks which demonstrated key LLM pipeline concepts such as tokenization, vector embedding, and vector similarity comparison. In this video, we'll build a full-stack app with React on the front end and FastAPI on the back end, which will implement these concepts. Before we dive into the code, let me give you a quick demo of the functionality. This app provides search capabilities for products in an outdoor adventure gear outfitter catalog. When the app first loads, there are no products in the vector store. So I'll seed the vector store with some sample products as we see here. Now I'll go back to the search screen and search for a lightweight tent. And we see the search results with similarity scores. Also, if I scroll to the top and click the Show Tokenization button, we see the token breakdown of the query text I submitted. The app also supports image search, as we see here. Now, back in the admin view, I can add a new product to the vector store. After creating the product, we see the total product count went up to 21, and cooking products is now at 6. And now I could go back and search for a Dutch oven. And we see our new product. Finally, the pipeline demo shows how semantic search works, from text input through tokenization, embeddings, and similarity search. So if this seems like something you're interested in building, let's get started. First, I want to mention that I'll put a link to the GitHub repo with the code for this project in the description below. If you jump into the repo, then the 2LLM demo app folder, you'll see all the code for the app, as expected. But I also want to point out the Agents.md file. An Agents file is a standardized markdown file placed in a software project's repo to provide instructions and context specifically for AI coding agents. It acts as a README for AI. It streamlines AI workflows by centralizing project conventions in one human-readable, agent-understandable file. And you use the Agents markdown file by prompting your AI coding agent to read the file and follow its instructions. Now, I had Cursor create this Agent.md file after I built out the entire project that we're going to walk through shortly, so it's closely aligned to a particular implementation. Typically, you define your agents file at the very beginning of a project before any code's written, so that it can act as a source of truth for architecture decisions, coding standards, file structures, and implementation patterns. But I just wanted to create this to demonstrate how to use an agents file with your coding agent. And believe me, as good as coding agents are, it wasn't as simple as just asking Cursor to create this file. In all honesty, it took about half a day working with Cursor to get the agents file where it needs to be to build this project properly. Now, if I launch my coding agent in Cursor, I could give it the following prompt. Please read the agents.md file in this directory and build the entire project from scratch according to its specifications. Follow the file exactly. It contains all the information needed to implement this outdoor adventure gear catalog search application. Start by reading agents.md, then create all the necessary files, directories, and configurations as specified. When checking the shell scripts at the end, please verify all services are deployed and working properly before seeding the data store. If there are any errors, fix and evaluate again. And with that, it'll start scaffolding the project. Now, I'm going to fast forward and skip to the end of the scaffolding process because it does take a while, but we'll slow things down again when the agent gets to running the shell scripts to deploy, test, and tear down the app. Okay, the agent has written all the code and is now running the deploy shell script, which it also created to launch the app. Here we see the ChromaDB vector store has been created when the agent populated it with the seed data, and now it's running the destroy script to clean up after testing. So we're ready to launch the app ourselves by executing the deploy script in the terminal. And now we could hit the FastAPI's docs endpoint and test it. And now we could load the UI. Back in Cursor, if we open the architecture.md file, which the agent created, we see a very high-level architecture diagram. Of course, we've already mentioned that the front end is built in React and the back end is a FastAPI server. But under the back end server, it also lists the models and vector store used in the LLM pipeline. If you watch the prior video in the playlist, you'll recall that the sentence transformers all mini LM L6 v2 is a popular and efficient pre-trained transformer model that converts sentences and short paragraphs into dense numerical vectors, or embeddings, for tasks like semantic search, clustering, and information retrieval. It offers a fast, high-quality alternative to larger models by compressing semantic meaning into a 384-dimensional space. The Salesforce Blip Image Captioning Base is a powerful pre-trained deep learning model from Salesforce. It's based on their Blip framework, or bootstrapping language image pre-training, designed to generate descriptive captions for images, understanding both visual and textual information effectively for tasks like accessibility, content moderation, and general vision language understanding. It excels in converting visual input into coherent text. So basically, Blip enables image-based search by converting images to text descriptions that can then be embedded and searched semantically, just like text queries. ChromaDB is an open source vector database designed for efficiently storing, indexing, and querying vector embeddings. It's specifically built to power AI applications such as LLM apps, semantic search, and recommendation systems by enabling searches based on data meaning and context rather than exact keywords. For us, Chroma is the vector database, the vector store, used for storing and searching product embeddings. It serves two purposes. First, it stores the product embeddings as 384-dimensional embedding vectors for each product, as well as product metadata like name, description, category, alongside the vectors. This data is persisted to disk in the .chroma directory in the backend apps directory. And second, Chroma performs similarity search. So when you search with a query, either text or image, it finds the most similar products by using cosine similarity to compare query embeddings against stored product embeddings. It then returns the top K most similar products, or the number of most relevant or closest results, ranked by similarity score. Moving down to the data flow section, we see flows for product creation, text search, and image search. Scrolling back up to the product creation flow, we see from the admin panel, products can be created by providing relevant information. When a product is submitted, a placeholder image is created on the back end and stored in the static products folder. An embedding is generated from the description using the all mini LM L6 v2 model, and data is stored in the ChromaDB vector store. The search by text flow obviously begins with a user query. On the back end, the query is turned into a vector embedding. ChromaDB performs a similarity search using cosine similarity and then returns the top K results. The search by image flow starts with the user uploading an image. We do some validation on the image. Then Blip is used to generate a caption from the image. Then an embedding is generated from the caption. A cosine similarity search is done in Chroma, and again the results are returned. Now there's more info in the markdown file if you're interested in reading through it, but we've covered enough to move on to looking at the code. And we'll start in the backend folder. For now, we're going to walk through the generated files, just to get an understanding of the processing. Later, we'll actually create a project from scratch, adding our own code. So if you don't want to follow along with the walkthrough, feel free to skip ahead in the video. Looking at this diagram, we see the front end makes a request to the FastAPI backend endpoint, which is defined in the API.py file. Business logic is implemented in the admin and search Python files, and the AI models are used in the embeddings and captioning files. And search.py also contains the ChromaDB vector store integrations. So let's follow the flow of a user clicking the Seed Data button in the admin UI. Here in the API.py file, we see the registered endpoints, and there's a post endpoint to /admin/seed. The seed database function defines a data file which is populated from the seed products JSON file, which if we look in the data folder, we see here. It will load the data into a products variable, and then for each product data in products, it will call the create product function, passing the product's properties. Going into create product, which is in the admin Python file, we see this function creates a new product with generated image and embeddings, and returns a dictionary with the product's ID, name, description, and other properties. So here it's generating a unique ID for the product ID, and then if needed is creating a directory on the back end to store the generated images. It then generates and saves an image for that product. And just to be clear, the generated images are actually placeholder images with text displayed in the UI, which is good enough for the demo. Then it calls encode, passing the description to create the embedding. So if we open encode, which is in the embeddings Python file, it first calls the getModel function, which returns an instance of the sentence transformers all mini-LM L6 v2. Then it calls encode on the model, passing the text and storing it in the embedding, and then returns the embedding as a list back to the calling function. The metadata is then created, and then the embedding, the metadata, and the product ID are passed as parameters to the add product function in search Python, which first calls the getCollection function, which gets the ChromaDB collection, or creates it if it doesn't yet exist, then calls the add method on the collection, passing the embeddings, the metadata, and the product ID. Then the product dictionary is returned, and we loop again for the rest of the product data in products, and ultimately return a response, if we're successful, with the number of products created. And if you recall from the demo, when we seeded the products into the vector store, the number of total products and the count of each products in each category were displayed. And that's done by making a GET request to the backend's admin stats endpoint, which calls getProductCount in the search Python file, which gets the ChromaDB collection and returns the count, which sets the value for the total number of products. And then for each category, the getProductCountByCategory function is called, which gets the collection and the count, then gets all products from the collection, then traverses the metadata to populate and return category counts. And then the data is ultimately returned to the client. Taking a look at the search post endpoint for a search by text query, a query embedding variable is populated by calling encode on the request query, which is in the embeddings Python file, which first gets the model and then calls encode on the model, passing the text and returning the embedding as a list. Then the search products function is called, passing the query embedding and the top K results to return. And search products calls query on the collection, setting the query embeddings property equal to the query embedding passed into the function, and end results to the top K. Then if result IDs were found, it gets the metadata and the distances, which represents how closely related the two vectors are, then converts the distance to the similarity score and creates a product with its properties, appends the product to the products list, and then ultimately returns the list. Then the results are populated and returned with the query caption. When a post request to the search image endpoint is hit, we get the image and then pass it to the generate caption function in the captioning Python file, which will get the model and the processor from the getModels function for the Salesforce Blip Image Captioning Base Model. We then pass the image to the processor to get the inputs, and then call generate on the model to generate IDs and pass those to the processor's decode function, which generates a caption, which is then returned to the calling function and then passed into the encode function, which gives us the query embedding. Then we could take the query embedding and call search products, returning the results with the query caption. Now, before we leave the backend code to look at the front end, I'll point out the debug endpoints which are used in the LLM Pipeline demo UI view, which we'll look at later. Okay, here we are in the front end folder, looking at some code for the React app. And I'll say up front that I'm not going to dive deep into this code, because you could really use any front end you'd like. You just have to hit the backend endpoints and pass the appropriate data for each request. That being said, let's start by following the flow of the app when it's launched in the browser. First, the user hits the front-end app's URL and the index page is served. This has a script element of type module, which points to the main TSX file in the source folder. A React TSX file is a TypeScript file that contains JSX, JavaScript XML. JSX allows us to write HTML elements in JavaScript and place them in the DOM without any createElement or appendChild methods. Here in the main TSX, we see the app element, which is a React component instance, and it's imported from the app TSX file, which serves as the root component for the entire application. This file has code for displaying the navbar, the search page view, and routes for the search page, admin panel, and the LLM Pipeline demo app views. So in the route section of the app TSX file, for the route with the path of a /, which is the root route, the element is pointing to the search page. So this is the element which is loaded by default. And up here in the search page definition, we see in the page container div, it displays a search form and the results. And the search form is in the components folder, and that's the search form TSX file. In that file, there's a handle search function, which if the search type is text, will pass the user's text query to the search by text function, which is in the API TypeScript file. This function passes the user's query and the top K in a post request to the server's search endpoint. When the server responds, the response is passed to the handle response function, which gets the status text from the response and returns it as JSON. This is then returned to the search form as an object conforming to the search response interface, whose results property contains an array of objects conforming to the product interface. So back in the search form, when we get the response, it's passed as a parameter to onSearch, which is a property of the search form in the app TSX. The search response is then injected as the value of the search response property of the results view, which maps the results of the search response into products, which are then displayed on the page. Now, to wrap up our review of the generated code, I want to jump back in the API Py file in the backend folder and look at the debug endpoints. Again, these endpoints are used by the LLM Pipeline demo view in the UI to get the data for displaying the tokens, the embeddings, and the similarity scores. Taking a look at the debug tokenize function in the debug tokenize endpoint, we see it passes the request text to the tokenize function, which is in the embeddings Python file. First, it gets the model, which is the sentence transformers all mini LM L6 v2, then the tokenizer from the model, and then tokenizer is called passing the text. Decode is then called on the tokenizer, then decode is called again, this time for the token IDs without special tokens. Then ultimately, the token ID, and the position are appended to a token mapping with additional properties set as the token mapping result and then returned. The debug embedding endpoint passes the request text to the encode function, which gets the model and then sends the text to the encode method, getting the embeddings and returning them as a list. And finally, the debug similarity endpoint generates embeddings for the text that were passed in using the encode function, then normalizes the embeddings to calculate the cosine similarity scores, which are then returned. So that wraps up the walkthrough of the generated code. I know we didn't cover all of it, but it should have been enough to get an understanding of how the app is implemented. Now, we're going to jump into a clean project folder in Cursor and build out a similar app from scratch. So here's a preview of the new app we're going to build. It's a simplified version of the app we walked through just to minimize the amount of coding we have to do, but it demonstrates all the key principles in the LLM pipeline. It uses a FastAPI backend and a Streamlit frontend, and implements functionality from seeding the vector store and viewing its embedding space, to running the pipeline and displaying the tokenization, embedding, and similarity search results for the query. Alright, I'm in an empty project workspace in Cursor, but before we start coding, I want to mention that you can find all the source so you can copy-paste in the 2 LLM demo app v2 folder in the project repo. Now, I'll launch a terminal, make an app directory and change into it, then run the uv init command specifying Python 3.12, then run a uv sync. Now I'll add the dependencies for FastAPI standard, sentence transformers, and ChromaDB. Then I'll make a data directory and populate it with the seed products JSON file, as we see here. Now I'll create an init.py file, remove the default main.py file, and create a new embeddings.py file so we can build the embedding module. This will handle tokenization and converting text into vector embeddings using sentence transformers. I'll start by adding the imports, then creating a variable to hold the model. Then add the getModel function to get the all mini LM model from sentence transformers. Then I'll add the tokenize function, which takes the user's text query. We'll get the model and the tokenizer, then pass the text to the tokenizer to tokenize the text. Then encode the input IDs, which are returned. Now we'll get the tokens with special characters by calling convert IDs to tokens on the tokenizer, then build the token mapping with the token string, token ID, and the position. Then return a dictionary with the token's properties. Now I'll add the encode function, set the model, call encode, and return the embedding vector as a list. The getEmbeddingStats function will take an embedding, then use NumPy to convert the embedding vector to an array, then return a dictionary with the properties we see here. And that's it for the embeddings Python file. Now I'll create a search Python file so we could build the search module. This uses ChromaDB as the vector store and handles seeding products, searching for similar items, and retrieving embeddings for visualization. Again, I'll start with the imports, then get the path for persisting the ChromaDB vector store. I'll create variables for the Chroma client and collection, then define a getCollection function that will get or create the ChromaDB collection. Now I'll add a getProductCount function and a function to seed the Chroma database, which takes a list of product dictionaries. It will traverse the list, and for each product, it will call encode, passing the product description to create an embedding, then create a dictionary to store the product metadata. And the embedding, metadata, and ID for each product are added to the collection. I'll define a search products function that will search the vector store based on the query passed in. It will call the encode function, passing it to query to create the query embeddings. Then call query on the collection, passing the query embeddings to get the results. Then it'll traverse the results, creating a product dictionary for each result ID found, then return the products. The getAllEmbeddings function will return all products and their embeddings for the vector store visualization. And that's it for the search Python file. Now I'll create an API Python file, which is the main API module for the app. It's the FastAPI backend and will have 6 endpoints: health check, seeding, tokenization, embedding generation, search, and embedding retrieval. Here I've defined an instance of the FastAPI, created text request and search request classes, which are Pydantic models. I'll add the health check endpoint and the seed endpoint, which passes the products read in from the seed products JSON file to the seed products function. The tokenize endpoint, which passes the request text to the tokenize function. The embedding endpoint, which passes the request text to the encode function, then passes the response from that call into the getEmbeddingStats function. And the search endpoint, which passes the request query and top K to the search products function. The embeddings endpoint, which calls getAllEmbeddings, returns the embeddings for visualization. And now we can launch the app and test it out by loading the Swagger UI. First, we'll test the health check. Then the embeddings endpoint, which we see returns empty arrays since we haven't yet populated the vector store. So we'll hit the seed endpoint next, and we see that was successful. So let's go back to the embeddings endpoint again, and now we see the expected data. Then finally, we'll try a search, and we see our results. So that's it for the backend code. Now let's take a look at the code for the Streamlit UI. First, I'll open up a new terminal, so we'll be able to launch the UI while the backend is running in the other terminal. I'll install dependencies for the front end, so Streamlit for the UI, Plotly for visualizations, and UMapLearn for dimensionality reduction. Then I'll create the Streamlit app Python file. I'll start with the imports and basic page configuration to set the title and layout to wide for better visualization space. Then I'll add the sidebar with the vector store controls. In the main content area, I'll add a text input field where the users can enter their search query. Now I'll add the pipeline button and set up the 2-column layout. One column will show tokenization, and the right column will display the embeddings, the stats, and the histogram. The search result section is next and contains the comparison line chart, cosine similarity metric, and the results bar chart. And finally, I'll add the UMap visualization that shows all products in a 2D embedding space. So with the front-end code complete, we can launch the Streamlit app and open it in the browser, and we see our UI. Since we already seeded the vector store during the backend testing, we can now view the embeddings. And looking at the plot, we see that similar items are grouped together in the vector space. And finally, we can run the pipeline and see the results. So this looks pretty good, right? Well, not exactly. If you look at the Streamlit code, you'll notice that we're importing the dependencies for the LLM pipeline tasks directly and calling them in the code. We're not actually using the FastAPI backend. So let's make those changes now. And I'm going to use a git diff to show the changes to you because I think it's easier than modifying the code directly. But just to note that the changes you see here will be the code that's committed to the repo, since we obviously want the front end calling the back end. Okay, looking at the git diff, the code on the left side, the line starting with the minus signs, is the old version, the version of the app where Streamlit didn't call the FastAPI backend. And the code on the right side with the plus signs is the updated version, with Streamlit calling the backend. Lines without plus or minus signs represent code that wasn't changed between the versions. So, starting at the top, on the left where the minus signs are and the code highlighted with the red background, we see we're deleting the imports from the embeddings and search modules, as well as JSON. And on the right, where the plus signs are, and the lines highlighted in green, we're importing requests, then adding a variable for the API base URL, which points to the FastAPI server, and then helper functions, which use requests to hit the backend endpoints for the functionality we need. Here on the left, we're deleting the code that calls the seed products function directly, and on the right, we're calling the seed products from API function declared above, which calls the seed endpoint. Similarly, for tokenize, we're removing the call to tokenize from the left and using the tokenize via API function to hit the tokenize endpoint. We do the same for encode and the embeddings, as well as for search products. In the vector store visualization, we remove the call to the getAllEmbeddings function on the left and call the getAllEmbeddings from API function on the right. And those are all the changes that we need to make. Now let's launch the app and ensure it works as expected. Since there were no changes to the backend, we could leave it running in the first terminal. Then we'll relaunch the Streamlit app, then open the UI in a browser and see the results. So that concludes this demo on building an LLM pipeline, which demonstrates tokenization, embedding generation, and vector similarity search. If you found it interesting, feel free to give it a like. And if you'd like to be notified when I add more content to the channel, please consider subscribing. In the next video, we'll dive deep into prompt engineering, but not as prompt tweaking, but as an actual engineering discipline. I'll show you how prompts act as runtime configuration, how to constrain outputs, and how to make LLMs behave predictably in real systems. Finally, if you have any feedback on the video or would like me to make a video on a specific topic, feel free to leave a comment. Thanks for watching.